Okay, good afternoon, everybody. Thank you so much for joining on the Friday afternoon. I see a couple of people more coming, so let's go. Once again, very good afternoon, everybody in person and everybody on the Teams webinar, Dr. Ati, and everybody, all my students and distinguished guests. So it's a real pleasure to have Dr. Kaan Oxbay from New York University to be with us. And he has strictly told me not to, say too much about him. He is too humble. So he is the director of C2 Smart and now the C2 Smarter Research Center in NYU. And he was a professor in Rutgers University, and then he moved to New York University and the Center for Urban Science and Progress, very accomplished. So I'll let him take the stage and speak about his research on AI and digital twins. Dr.
Thank
Osman.
you. Thank you. So thank you again for coming Friday afternoon. When I was a graduate student, the seminars at Virginia Tech was the high point of the week because they had pizza and it was Friday afternoons. So, and the first semester I put on like 15 pounds, I guess, just going to seminars. So don't do that. All right. And I could never lose it afterward. Anyway, so thank you very much for coming. I also want to thank Shaurya for his hospitality. Since yesterday, he really spent a lot of time with me. And also Professor Abdelati and Professor Naveen, Professor Shamil, and then Professor Nejati Chatpash for spending time with me, eating lunch, dinner. So I'm ready to talk and burn some calories, I guess. So I actually this morning, Shaurya gave and his students, they're here. They gave me a quick presentation of what they've been doing. Very impressive. There's a lot of overlap. So I will go over certain things, but I also want to give you kind of an idea of our thinking and kind of the progress in our thinking in terms of smart cities and digital twins. And stop me if you have a question. I don't have to cover all the slides. Like any good professor, I have more slides that I can talk in detail, but just ask me questions. So no problem. So okay. So let me just. This is not working now. Sure, yeah, what happened?
Yes.
Maybe I should do it this way. Okay, so now I can do it. So I mean, just a very quick introduction to our center. So some of you might be familiar with this University Transportation Center. It's federally funded. So this is our second term. It's every 5 years, and NYU is the lead for this one. The reason I'm showing this because many of our research is driven by the center's team and center's members. As you see, we have several members, some local, some not so local. So University of Washington, Seattle, for example. And then we also have a number of local partners. And then we are doing work basically on the cities. So the reason, if you look at all these universities, they are in certain type of city, small, large. So New York obviously is the largest city in the country. But our goal is basically whatever we do in one city to see if it's applicable to another city in terms of traffic control, incident management, incident detection. So that's kind of how we think about what we do. Okay. So the other thing that we would like to think about, unlike some transportation, so I've been around many places, so we always talk about it, but we never do it. One of the ideas we want to do is system of systems. That means I would have loved to see here more people from non-transportation background. Anybody from non-transportation background? Okay, that's very good. So basically, for example, my closest partner is a structural engineer, a bridge engineer. Okay, so what do you know about bridge? Of course, like most of you, I took the courses as an undergraduate. But if you want to replace a bridge or do construction, that has effect on the transportation system, not only on the roadway, but also on the transit, because I might need more transit, on air pollution. So we want to think in terms of systems, how we can design solutions not only for transportation, but for the whole system. In fact, this is easier said than done. So if somebody tells me this, kind of do it, I would say, no, I can't do it, which I recently told to my dean. He's a big systems guy. Because it's difficult, but it's, I think, how we want to think. The other thing is very interdisciplinary. So as you see, these are all schools in NYU. Some of them you might have already heard, like business school, Stern, Courant, Applied Math. So we work with them because there are certain things, I was telling Shoria this just a few minutes ago, there are certain things we don't know very well how to do. We need a mathematician, we need a computer scientist. So we would really like to work with different centers in the university. So that's also something that I push hard, because as academicians, we like to sit in our rooms and then do our own thing and don't want to talk to anyone. But we want to change that. And this funding center allows us to do that. All right. So now I'm going to talk a little bit about digital twins and then go to our work. So, this is an idea that you will see next slide, not a new idea, but it became something hot. Like 10 years ago, it was big data. Everybody was talking about big data. Then it's AI. Then this digital twin. So there's like two definitions. And I use the industry definitions because really most of these things are driven by the industry. Like big companies like Deloitte or IBM, because they have the marketing power to do this. And then if you look at this, I asked my student to tell me like what do they talk like in general? What are the different components? So we found out that of course there's a physical system, there's a virtual representation simulation. Actually, this part is the part that we are the most familiar with. The transportation engineers, we've been doing this virtual representation for a long time. Data acquisition, basically sensors, computation. You need to have computation to run all this data, simulation models, but also communication network. So one of the things that I think made this digital twin so exciting is 5G, because now you can move large amounts of data, which was not possible a couple of years ago. Of course, there's fiber, but fiber has its own difficulties. And also the visualization, user interface, interaction, so AI and computer graphics, all that play an important. So you see different components of digital twins. It's basically the right time to have this full system deployed. Although the individual parts, they've been around. So the idea is kind of how we put all of that together and what do we do to make it work. So the key word here is to make it work, because as a whole, as a system. Okay, so this is kind of a very non-scientific way of looking at the history. If you go at Wikipedia, they say actually NASA, which I heard that they're here. Not I mean I know they're in Florida, but in this university they're very strong. This space and so on. They did some kind of digital twin when they twinned the actual hardware with the simulation of it, and then a professor in University of Michigan came up with the name digital twin. This is very important, like big data. Everybody knows big, everybody knows data, big data becomes big. So anyway, and then there's some papers coming up. This one is from NASA. Since 2020, as I said, with AI and 5G, this became a real hot topic. Right? So this is kind of a very simple timeline. But then I said, okay, I remember, like we've been doing this kind of stuff. So for those of you who have been around, not many of you, actually, Federal Highway and U.S. Department of Transportation have been working on similar systems for a long time. So these are two projects that I was involved as an external evaluator. So this is so-called integrated corridor management. Exact same idea. So you have the sensors on a highway corridor. You have the sensors. You have different functionalities like incident management, incident detection, lane closure, work zones, name it, all kinds of stuff. And you have a simulation of that corridor. And then actually Federal Highway tested this kind of systems in real world. And we were actually looking the outcome of that. So one of the projects that I was involved with, They have adaptive traffic control along a urban corridor. And then when there's an accident, they run the simulation in the background. Simulation tells them what to do in terms of the signal timings. And then they change the signal timings or not. Okay, so some of these projects, they've already been here. So it sounds like exactly like digital twin, but they were pilot projects. This is a little bit on the more static side. So basically on simulation based, but it's looking at the traffic simulation and also large scale urban demand forecasting simulation. Okay. So now, again, here you can think about it. Digital twin doesn't have to be online and real time. It can be offline. So this is kind of an example of the offline, this guy. So we have different scales of simulation models. We are running them. We are also observing what happens in the real world. Not necessarily through sensors, maybe offline counts, surveys, whatever data we get, and then we feed it back into this system and then see if the system is telling us a good forecast or not, and then go back and do this. But maybe the time frame for this one is next minute, next 30 minutes, this is next year, next 5 years. But so digital twin doesn't have that kind of definition that it has to be real time or it has to be offline. It can be different time scales, but it has to interact with the real world, right? So if you think about now everything that I said in transportation, actually, we can have digital twins, and we have some of them for different kind of applications. So this is public transportation. Traffic management has been kind of in the forefront of that, more in the real time. For emergency disaster management, I don't know if there's anyone here. We've been doing that a lot, looking at models of evacuation using large-scale simulation or flood and other impacts, and then seeing what happens in real world versus what the digital counterpart predicts. And then this is for urban mobility, for planning, for construction, and so on. And actually, we have done quite a lot of work on construction planning and traffic simulation combined. Okay, so this makes sense? All right. So then I wanted to go back to our work. In fact, we've been doing that kind of digital twin business. The first book I wrote with Shaurya's advisor, Professor Kaan, on incident management, and this was exactly the idea. We run a background model, and then the model tells the traffic operator what to do, and the operator does something. We observe what happens to traffic, and then we run the model again. All right. But when I was doing this is like prehistory. There's no real internet. Okay, so there's kind of email, So the Federal Highway gave us $200,000 to build a system like that. But I cannot run this on the internet. So I say, you and you, we sit in this room, and then I take two other people in the other room. Okay, so we kind of simulate like a movie. So Federal Highway guys come, okay. So this guy says, oh, there's an accident. So he enters, there's an accident. So this guy in the other room, he runs the model. He says, okay, then you have to change the traffic signals, and then emails this to the other guy. So we made a movie like that, okay? And they loved it. But they said, this is, how are we going to do it in real world? But we were thinking about digital twins before the name digital twin existed. Then we also moved and looked at feedback control or dynamic traffic assignment. It kind of took away that operator. Basically, it could make the decision on a feedback sense in real time. Then there's a couple of other things. So the ones you see in the bottom, those are like more recent work that I've been doing. This is exactly the same idea, but now we inject connected vehicles, trajectories from the connected vehicles, AI. And this is the project I was telling Shaurya, one of them here, is like looking at the AI and digital twin type of technologies for DOT use. So again, the idea is not new, the name is not there, but we've been thinking about that. So in that line of thinking, I am part of the traffic simulation committee at TRB. We need young members. It's ACP 80. So we did this Sunday workshop twice on digital twins. And actually, again, the simulation committee members, some of them, they said, oh, we don't need that. I said, really, we need it. So we kind of did this, and it was a big hit. I mean, I don't want to advertise for it, but I was surprised too, because I was like this room, I thought like only 10 people will come, because the first one was on a Thursday, the last day of TRB. And the room was full because it looks like people were interested, right? So again, that kind of helped us to talk to the people from our community, what they think about digital twin and how we had to move forward. Okay, so now this brings me to our work. And again, this kind of part is almost 2.5 years of work. Of course, I showed you the background. There's many, many decades of thinking, but this is one of my postdocs and PhD students trying to put these ideas in a kind of new digital twin sense. So the first thing is, the way we see it, for the digital twin to happen, we need to have sensing, smart sensing, okay? And this is still a problem. We're not, so we call it observability. We need to observe the network, the traffic. We still don't have that. In New York City, we don't have any sensor that will observe volumes. This is the largest city in the country. We don't know the volumes, right? Then we need the system perception. This is a new word for basically system identification, or looking at the state of the system and so on. And then, unless you do these two things, you cannot come to digital twins in our thinking. So you need to kind of combine them, right? So here, kind of the framework, but I think the most important part here, I mean, these are all like kind of parts of digital twin touched, but we have to get this data and do that data analytics and analyze it. And then we need to turn this into some kind of decision making, and that's what I'm going to spend some time on. Okay. So this is, I'm going to go. So what we said is, since we don't have the sensors, and since sensors are always difficult to deploy, ground sensors and other kind of, can we use the cameras, all right? And if you look at the cameras, actually you can use them for many things, from curb monitoring, pedestrian detection, to flood detection, and name it, all right? But you still have to have the cameras. So I'm a little late, but so basically, for example, we have a project, but there's a problem with using cameras. We have a project with Meadowlands. Anyone heard of Meadowlands? That's like a big stadium in New Jersey, and the World Cup will happen at Meadowlands in 2026. So we want to basically monitor the disturbance caused by the World Cup matches around Meadowlands, and do the digital twin of that to manage the traffic, all right? But they don't have cameras for traffic. So we wanted to test it, to test two cameras. Cameras are donated. And then I want to install them next week. So they said, we cannot install it. The Meadowlands administration, they said, you have to find your own electrician, right? Fine. So guess how much it costs to install two cameras on a like a regular pole on a road around the Meadowlands Stadium? Just make a guess. 1,000? 2,000? 10,000? This is like a art thing, like whatever. Okay. They asked for two cameras, $18,000. Yeah, and then they said this doesn't include removing them. So I told my student, I said, just find me a leather. Okay, I lost some weight. I'm a little bit more like flexible. I'm going to install them myself. She says they'll shoot you because you need to have license. You cannot do it. So $18,000 for two cameras. If you want to do the real system, you have to install probably 15, 20 of them. Okay, so 2,000 was very low. So, so what we came up with recently, especially during COVID, because we're all bored at home and we don't know what to do. Students cannot get out. I said, let's do something interesting. Can we use the existing DOT cameras that provide public feeds like this one through their website? So can we really capture those feeds? And New York has 900 plus closed circuit traffic cameras. They said, okay, we'll try. So basically, we started grabbing this information from New York City cameras and processing them. And we use them first to understand pedestrian movements. Because during COVID, that was the hot thing. No? If you have too many people around an intersection, that means they're not listening to the government. So we're not going to report them, but it tells us something. So basically, we build some kind of a pipeline to get this information and to process it and to use mainly public cameras and off-the-shelf image processing software like YOLO, right? I mean, with some human customization, it was quite successful. All right, so this is some pictures, some from New York, some not. Okay, so this is New York, this is New York. This is actually something that we created for vulnerable users to label them. So we don't have enough vulnerable users. So we asked a couple of students to act like an old person with a cane or with a chair and so on. And then we recorded that. So this is basically most of the data comes from New York. So this is Lucello. So he's like acting like an old person. So we kind of found out that with a little bit of customization, we were able to capture the movement of the people quite well. The difficulty we have, most of these cameras, the quality of the image is very low, and the field is very low. So there's not enough movement. But even with that, we were able to do a good job. So this is now when we were successful with that. This is the sensing part. Other agencies started to come to us. This is the Port Authority, and they have a camera here, and they share their camera feed with us so that we can capture the queues at the terminal. Okay, so this is the same thing, and this is from New Jersey Turnpike. This is their cameras. So one good thing is that we are not installing new cameras. We are using the existing infrastructure. And there is no IRB or nothing because this is publicly available information. So we are not really, we are using what everybody else is using. Okay. So there's an IEEE article on this, and you can go and read more details on that. Okay. So now we want to do a little bit more advanced stuff. So basically, we want to detect work zones and then look at the impact of the work zones. And believe it or not, New York doesn't have a way to track the work zones. So you get a permit for 6 months, and during that 6 months, you can do the work zone work whenever you want. But we have 1,000 cameras, so maybe we could catch some of those. But when you catch them, now this is different than your image processing, regular image processing, because you have to understand if it's a real work zone, if it's an active work zone, how many people you have, and so on. So this is an IEEE paper, ITSC paper we published in identifying work zones with all these features. Okay, so this is how it looks like, and then we are focusing in Manhattan. And as you see, at the cones, we develop the kind of shape of the work zone, and then by looking at like who is in the work zone, what kind of person, and so on, we decide if it's an active work zone, and so on. So I mean, you can go read the papers. There's a lot of good details on how you do the feature selection and so on. Okay, so I'm not going to show you this whole video, but then we build an app on top of this. So basically, to capture from the cameras whatever we can see, all the work zones we see, and also look at the permit data that is entered, as I said, for 6 months by the contractors, and try to match if the permit data matches with what we see from the video. So any guess what kind of percentage match we saw? How much? 100? Okay, don't quote me on that, but this is like almost zero. So because most of the work zones are short work zones, all right? The big ones you anyway know. So like the power company goes and wants to change something. Okay, they put the cones and then they do the work for a couple of hours. They don't even have the permit, most probably, or the permit data is not entered the right way. You know, so So the match was not very good, but at least we have all these databases together, and as you see in the movie, we could kind of record what we see and understand the duration of these work zones and what kind of work zones there is. And you see, this is taking me to the next level, because now I'm going to use this information to better manage traffic and the effects of work zones. Okay, so this is the big database, and we call it AI Urban that we built. So this is very similar to what Shorio was doing with his LiDAR database, but this is like for the whole New York City. We have everything else that we talked in this database that you could see. Right? Now, the system perception part. So we have all this data, but we want to use this data to do something, okay? Something useful. So here I'm going to talk about a research idea. So what I'm going to talk about, I cannot do it, but if I could do it, it would be really nice. So these cameras that you see, they can pan and tilt, and you can move them, but they're rarely being touched. I mean, they only touch them when there is an accident or something happening, okay? And most of the time, when they know something happening, it's too late, they won't even do anything with it. Right? So we basically said, what if we can have a way to control these cameras to maximize the information we get from the cameras in terms of understanding the traffic conditions and the impact of some events like work zone or accident around that area. Okay? So this is tried not in Manhattan, in Brooklyn, downtown where we are. And then we use the cameras over there. And as I said, the camera, we assume that we can control the camera remotely to kind of focus on where we want to focus. All right. And this is a part C paper. Basically, there's a game theoretical framework where we try to maximize the information by changing the position of single camera or multiple camera at the network level or at the root level based on some learning process in a game theoretical framework, right? So this is kind of overall how it looks like. So the camera can only look at one direction. So we have to decide which direction it will look, and then we can get data. We can get its position based on the network level optimization, root level, or link level optimization, and then provide information to the traffic managers. Okay, so there is so what you see here is I have information only at one direction. So what do I do for other directions? And these are kind of my loss functions. So for the network level and link level, I'm trying to minimize the difference between observed volume and historical volume. For the root level is the travel times for different reasons. So we tried different loss functions. So those are the loss functions that work the best. So the idea is I observe whatever I can observe the optimal way. For places I cannot observe, I'm going to use a neural network-based estimator to estimate these volumes based on what I observe now and the historical data. Right? So this way, it's like a data imputation. I impute the data that I'm missing based on historically trained neural network, and then what I observe just at this point. Okay? So this is basically a very typical encoder-decoder type of algorithm that we use, and then it's a spatial temporal prediction. So basically, there's a time series I'm looking. So I'm looking at t, t1, t plus 2, blah, blah. But I'm also looking at spatial correlation between the links to improve the weights for the prediction. So the deep learning model can do that for me. Again, this is a part C paper. All right. So, so this is basically some very interesting results. So if I just use the camera, I have large errors. And actually, it's always for the similar kind of network volumes. So the volumes are not, I'm keeping the same volumes. But if I add the prediction algorithm on top of the observations, the errors are decreased considerably. So I can really improve my understanding of the state of the system perception, extremely well if I use the camera observations that are optimized with the neural network estimate predictions. Okay, and this is kind of a toy network that we tried. So if there's a road closure around here, which was the best route from going 12 to 8, now you have to reroute the traffic. Okay, so if I just use the camera modifications and the real-time observations, I cannot really get very good results because I don't have enough cameras to detect the closure and the effect on this link. But if I combine the estimator with the camera, then I really improve my my predictions and routing. This is a little bit more difficult to explain, but this is kind of shows that the algorithm works. So when there's nothing happening, the camera is looking at different directions almost uniformly. But if something happening in one of the links, then the camera focuses on that link because in the optimization, you want to look at the location where there's problems. So we see a lot of focusing by the camera on that location. This is what we show here. Okay, so now I'm going to shift gears and talk about something that we've done very briefly. Okay, so you have this information and like a scenario, but we also want to think how we can use this camera information for the traffic managers more interactively. So one of my students, this is also excellence and prevention paper under review, second review. So basically, we are using this multimodal large language models to make sense out of the video data for the traffic managers. So basically, there's two prompts here. One is the text prompt, and one is the video prompt. So basically, you are feeding these prompts into any model like ChatGPT or Llama, whatever, and then trying to understand what happens in that image. Okay. And the paper is also available on our site. You can take a look at that. So basically, the innovation here is that we are not using a specially trained multimodal large language model, but it's like how we feed the information. So one thing that we do is we take the video and we make the video smaller portions based on some objective function. We decompose the video and then we feed that video portion separately, right? So what you see here is plain English, is that every video will have some kind of an output from the LLM in terms of what happens on that video. And what we use is the most safety or high risk response. So we forget about low risk responses. We just take the high risk response and then we use that as the response for that video from the LLM, right? The other thing that we do is we tokenize the input by using, again, off-the-shelf software to find the trajectories and detect the objects. So the LLM knows which object is involved in what kind of conflict. So it's not just looking at the pure video, it also knows vehicle 0, pedestrian 2, vehicle 1, pedestrian 2. We already labeled them before we feed them into the LLM. So there's some pre-processing. Okay, and then we get some output in terms of no accident, near miss, or accident. So those three things that we are asking, it tells us the scene content, it tells us who's involved, it also gives us some kind of a justification about the conflict. So where do I get this test data? This is kind of a video data that's generated, I believe, by Toyota. They use like actors to create high risk scenarios in like M-City type of environment, but they actually know what's going on because they labeled everything and they have explanation for everything. So we use that to evaluate our framework, and actually we got very good results compared to not doing anything. But the best improvement is that not only we know it's near miss, accident or no accident, uh, we know who's involved and what was the where was the conflict, which you couldn't do if you didn't do the pre-processing. Yeah.
So are you training a customized LLM based on the labels, or you are just using off-the-shelf chat?
Off the shelf.
Off the shelf.
Everything's off the shelf. Just what the pre-processing is on the video, and also the text prompt is based on uh, domain knowledge. So we're not asking what is the age of the driver, because that you cannot know. So we only ask things that we think that are useful and can be extracted. So the text prompts are predefined. There's a dictionary for text prompts. And for the video, there's pre-processing of the video that we feed into the LLM. But LLM is not retrained.
The way you ask is the key here.
Yeah.
The way you feed the videos and the questions that you ask. And what is the difference between these two videos?
Distance between what?
These two videos?
Difference, yeah. I mean, this is their video. I don't know the distance because I don't measure
And the difference.
Oh, difference.
Top and bottom.
There's no difference. This is basically same thing. This is here we are kind of identify. This is like here nothing is identified. By this we did the pre-processing, so we basically did the object detection and we're tracking the objects, and this is what we are feeding. So we are not feeding the raw data, raw image. We are feeding the image with identified objects and the trajectories.
So, for example, how much the accuracy of identifying near misses or crashes just by ChatGPT? Because it's a large language, so it's not trained.
The difference is it's 10% better. Not like
the
a
state of the art.
yeah. No. I mean, if you enter the raw video versus what we do is like 10 to 15%, so 55 to 70% accuracy. All right. But what the ChatGPT cannot tell me that car 2 is involved with pedestrian 1 at this location, because I entered all this process information, then it can tell me that. So I also know where the conflict happened and between whom. Right?
Why don't you fine-tune the large language model to this topic? I mean, it looks like the domain of the patient problem for the safety matter.
One is I'm lazy. Second, I don't have enough data to fine-tune it. I mean, even this Toyota data, I think it's like 50 scenarios. So I don't have enough data to train this for this problem. So, and I want to test if it works well with this pre-processing without me touching what they do, because they do 50,000 GPUs, all the information in the world. So I'm not arrogant enough to think that I'll do better than them. Right? But it doesn't mean that you cannot. I mean, so one thing that we are doing, I'm not showing here, is now we want to put another feedback loop, a person. They will look at the LLM's prediction or output, and then we'll give feedback to the LLM if it's doing the right thing or not, and if we can fine-tune it that way. We haven't done that yet. Right. So this is now the third part, is the digital twins part. So we built a simulation of downtown Brooklyn, and this is a very complicated network with incredible amount of pedestrian movement, vehicle movement, double parking, and so on. As we showed, we already have the cameras. We know how to process the camera information and all of that. So first thing we have to do, we have to calibrate the traffic simulation, okay? So that it kind of captures what we wanted to capture. So anybody here in this room worked on simulation calibration? Okay. Okay. Here, I mean, the innovation in this paper is that this is something that we've been doing for a long time. So the estimation prediction is different than many other calibration methods, but I'm not only calibrating for operational features. Why? Because I'm not only interested in getting the speed or the flow correctly. I also want to get the safety features correctly. And one of the safety features I know I can get, is things like time to collision or mean modified time to collision, one of these indexes. Okay? So I want to have a multi-objective function that I want to minimize when I do the traffic simulation calibration. Okay? So just focus on this one. So this objective function that I'm trying to minimize, looking at the volumes, travel times, and also trying to minimize the distance between the distribution of these time to collision frequencies with the real world data and with the simulation. Real world data, I had the trajectories. So I did get the time to collision numbers, frequencies from the actual trajectories, and I compare them with the time to collision numbers I get from the simulation. If they are too far away from each other, that means there's something that I need to change in the simulation to get this also correctly. But I'm not looking at the actual numbers, I'm looking at the distribution of these time to collision numbers because it's a kind of probabilistic problem. And then I use state-of-the-art federal highway measures to make sure that my predictions are within certain error bounds. I don't have too many outliers. I don't have too many inliers. And when I'm comfortable, I say that my simulation is calibrated. We use extended SPSA, stochastic optimization method, which is local. So it doesn't guarantee the global optimization, but it works quite well, actually. There are other methods that you can use, but they're very time-consuming and difficult. So SPSA needs only 2 points that I need to generate at each run, and it calculates the gradient, and it finds me some local optimal, which we assume is close to the global optimal. Okay, so I did that. Okay, and then I want to use now this digital twin that is calibrated to do a better traffic management. Again, in this case, my goal is not to manage the traffic to minimize travel times or maximize flow. I want to minimize the risk. That means I want to minimize near misses because I don't have a way of simulating accidents, but I have a way of simulating near misses. So can I minimize near misses, right? So I have one thing that I don't like about using AI and deep learning and so on is too many, abbreviations and too many different things. But this is very simple. So this part we talked about it. Here, I have a predictor of the traffic conditions from the current measurements and the encoder decoder model that I showed you. And here I have a Sumo simulator that I calculated. But Sumo, for the Sumo to predict what's going to happen half an hour from now, it needs an input. And that input comes from this predictor. And then I run the simulation, and I get the trajectories from the simulation, and I calculate near misses, MTTC, TTC, whatever I want. And I look if it is higher than average or historical, then I go make a decision in order to change traffic management so that my risk levels go down, and I keep doing that. And this part tells me how frequently I have to do this. Because remember, I'm running the simulator, and the STE part is fast because it's already a trained network. But the simulation takes a long time, especially for that complicated network. And then I have to take its output and convert it to the TTC. So I need to decide, do I have to do it every 5 minutes, every 20 minutes, every half an hour? And that's based on the error levels that I get, right? So this driver risk information comes into my sensing system, changes things in the real world, and then feeds back into the model. So this is what I told you in more like a time-dependent situation. Okay, so what you see here is not the travel times, not the volumes, but it's the risk levels. So the map shows you how the risk levels are changing over time. And of course, we have done many scenarios. So I mean, visually it's difficult to see, but if you do change something, you remove the work zone, you change the traffic signals, then the red will become less. Okay, and then here we just visualize how the risk levels are going to change.
Temporal evolution.
Yeah, temporally,
Temporal.
in time.
So do you see any seasonality or
This is only real time for like 2 hours.
for
So I'm not looking for the whole year or. No.
I think the audience wants the camera board, might get, they want to see.
Okay. Okay, so this is different scenarios. I'm doing the same thing for different scenarios with no work zone with one lane closed, work zone with two lanes closed, and then I'm like looking at how the risk levels are changing when I change the work zone type and so on. Again, you can try this for different things, just not work zones, maybe different type of accidents, different type of signals. So you can do this calculation for different kind of events and responses to the events. I mean, what you're supposed to see is if there is no work zone, so no lanes closed, lower risk. When you have one lane closed, higher risk. I mean, volume is just to show that we can calculate the volumes and that they're not like out of this world. So there's no relationship to the volume. So I'm not trying to show that. All right. Okay. So this is the last part. This is so as you see, I'm progressing. So now I'm looking at the digital twin, but this time we call it nano DT. So this is a very detailed level of digital twin for emergency operations. So the simulation is going to simulate emergency response. And this is something new. We don't have any results on this. This is based on a project that we got from NVIDIA. So they gave us the GPUs. But then I was told that to use those GPUs the most effective way, I have to spend $30,000 on a server. So I'm looking for that money. So, okay. So basically, this is kind of focusing not on the whole network, but portion of the network where there's a, let's say, accident of high severity. There's an injury or a building collapse. So I'm going to simulate that operations in detail and also get real world information and then do this digital twin idea. Okay, so we are using Carria for that, for this 3D simulation. And of course, one challenge is that not only we're going to try to simulate what happens given the current conditions, we also want to simulate different scenarios. Like if there is a parking lot, if I move the injured person to the parking lot, what happens instead of keeping it in the middle of the roadway? So we want to have multiple scenarios, and you can actually use LLMs to generate those scenarios in real world. And then we're going to try to do that, and that simulation will come from Carla. And whatever the Carla tells us at this local place, we will feed it into Sumo, and then Sumo will tell me what happens when I make changes to the incident management and emergency management. Okay, so no results. It's just started. So basically, this is the summary of what I showed. So we looked at like how we can use off-the-shelf software with existing infrastructure to monitor traffic. How can we use AI to make sense of that information and also use some game theoretical approach to maximize the information that we get? And then how we basically use the digital twin to understand the risk and make changes and decision making in real time. I'm running out of time, but I want to spend 5 minutes on the 2 slides after this. So basically, there's a lot of advantages, but there are also a lot of concerns. One is data quality, because the cameras that you saw, for example, they're not always the perfect cameras. The frequency of the images are not very good. They're not very well maintained. There are privacy and security risks. Also, we don't know how to best combine the information from other sensors other than the camera to make this digital twin to work much better. And then what is the accuracy we want? So my advisor, who was an OR person, he wanted to have 0.01 accuracy. Okay, I always like argued with him. I said the error due to stochasticity is like 10%, and you want to do like a 0.1%, but that was his world. So in our world, what is the level of accuracy that we want? 10%, 5%? So all these questions we don't have an answer. Okay, so this part is kind of completely not technical. So if any of you heard of Borges, this is one of the most famous writers of 20th century. There's a very small famous story that he wrote about um, a city that built a map, and then this map builders are obsessed, like we are now, with the digital twins and simulation, in making that map so realistic. And in fact, over time, the city became the map itself. So this is kind of a, for engineers might not mean much, but are we going to become, simulation is going to become the city itself. And when they did that, then there was no meaning of the place. So map and the territory didn't have a difference. So they decided to get rid of the map. So the map became useless. So I think something that we need to think about, like how accurate we want to be in terms of building simulation. And his story actually is kind of a, he's not a scientist, but he's seen this thing. And then there's a very famous French philosopher, Baudrillard, built on top of these ideas, the idea of simulation and simulacra. And I didn't put it here, but he used the idea that the world stops becoming reality. The world becomes a simulation, and we generated these things with ChatGPT, with LLM. So basically, the more you build the simulation, the more the world becomes like simulation. And then for people, the real world loses its existence. So imagine, for you to understand this, you are in an autonomous vehicle, and then the autonomous vehicle drives not like a human. It doesn't see everything like a human, right? So the world for the autonomous vehicle is very different what the world that we see. In fact, Baudrillard used the example of Disneyland. He said Disneyland is a world that doesn't exist in reality, but it actually exists. So this kind of a dichotomy. So
Yeah, I know. I've seen what it's done to my wallet.
so this is the example I gave you. So you can walk with a VR, AR type of thing, and you will see the world completely differently than I will see the world, right? So then we called it hyperreal, okay? And the signals, the signs, and everything will become different. What is the danger of that? So this is one, the student who did the LLM, he generated these figures. If you look at these figures, Rushuan, I said, like, what's wrong with that? Like, why do you think that there's something wrong with it? He said, Professor, look at this work zone. There's no real work zone like that. It's like cutting the whole, this maybe Park Avenue completely. So LLM generated this work zone, but it's not real. So as a human being, I can look and understand it's not real, but LLM cannot. So imagine now you depend on that with that VR, AR headset, and you start seeing the world this way. It's a problem. Like here, maybe there's nothing wrong with this work zone worker, but if you carefully look at the gadgets that he has, they're not real. They don't use this kind of gadgets and they don't mean anything, but the LLM generated those. If you look at the signals, you don't have traffic signals like this. So this becomes a hyper reality, or even reality that doesn't exist. And as human beings, we are capable of differentiating that, but we have to understand that we can't just depend on the simulation, depend on LLM or AI, because in the end, world is what it is. So we need to be careful in having that division between the model and the simulation and the AI. Otherwise, we'll be kind of losing touch with reality. So with that, I'm going to stop and take questions.
In the context of diesel traffic, that now is more autonomous, like a fully or partial autonomous driving, like Tesla and SD, which is not the traditional California behavior. Other models does not reflect the true mechanism of those driving pattern. So will this impact the driver model calibration, or is it a new like a new diagram or like new calibration methods to be applied? How do you consider that?
I mean, to me, the basic is the same, but you need to have different data. You need to have data of these autonomous vehicles, how they behave on their own or in relationship with other vehicles. But once you have that trajectory data or proximity data, it's an optimization problem. But without that, because even the car following model, it's a model, it's a black box. I don't even know how Sumo this thing does it. So I'm just looking at the output. So the optimization is based on the output. Now, the difficulty with the autonomous vehicle, can I go and tweak the parameters of the autonomous vehicle, or do I have to accept it as it is? Can't touch that. That I don't know. I mean, we didn't do that. Of course, probably can't touch it. You have to assume it's going to, until Elon Musk says, I'm going to change this. You cannot change it because it's his model, right? So that pretty much what I'm thinking. So if I hit the output, I can calibrate it and then make this changes that I can make to replicate what I see.
Yeah, the model itself, like the current model, like driving behavior, they are to consider all the human responses, stimuli response mechanism.
They're not correct, by the way.
Yeah, of course, it's not, but I think like an autonomous vehicle, they have different way of like perception, like making decisions.
Yes, and you never do that. I think the best way is think they're the flat box, and you cannot touch them. They'll do whatever they will do, like my kids. But then you have to kind of look at other things, you know. I mean, these are like commercial products, so you cannot really change them.
So just treat it as optimization problem.
Yeah.
Thank you, Professor. Very great presentation. Actually, I follow your see and step paper. Actually, in our lab, we try to make the benchmarking based on your baseline. Actually, anyway, I think it's great to we modeling the digital twin in transportation. But actually, like you mentioned, we have 1,000 of variables, like the camera output, one of the sensing signal, sensor observation. So each variable come with each formula, like you mentioned, the 0% accuracy on the, especially camera actually. Yeah, we develop a system for construction safety. And the problem here is always send the formula to the safety dimension. Like, okay, there's some problem with the construction site. 10 times, 20 times, 30 times, the safety dimension turn off the signal, turn off the system.
Yeah.
So I have the question that is there any, like, you have any like real life application of digital twin or system that actually work outside?
So that's why when I started on part C paper, I said, I cannot touch those cameras. It's a model, and it's so you're right. I mean, those cameras are not under our control. The hope is that the agency can see a value on maintaining those cameras and having better cameras, which actually now we're working. They got some smart brands, so they get better cameras, so it can maintain them, so that the information we get is reliable. Currently, they're not. So actually, a better model than what we have done would be to add those uncertainties, the camera failures, or the information that's not very dependable. And you want to turn the camera into the car. If you add those things, obviously there'll be more realistic assessment. At this point, we assume that all the cameras are working fine and can control them the way we want them. For work zone, it's more difficult because you might not have traffic cameras around the work zone, so you have to go put the work zone cameras. That's a different problem. I mean, it's a relatively better problem because you have better cameras, but you have to give enough time to put those cameras and so on.
We still have for now. Cannot solve it. We need to like put some uncertainty quantification there.
Definitely. I mean, so one of my students, the guy who do this is looking at uncertainty quantification for a black box image processing, any image processing algorithm. Turns out it's a difficult problem. Okay, but he might give up.
More questions? So we have a few questions on the chat. So Luis, she's asking that she has observed in industrial applications, Siemens and other companies, they have adopted some standard, and there are some products which are standardized for digital twin. But are there any standardized tools in transportation research that you've seen, or what is the reason we don't see any standardized?
I mean, not that I know of, but also the transportation world is very fractured. So there are different simulation tools. There are different ways of calibrating the simulation. I mean, a secret that everybody knows, probably 50% of the simulation models are not accurately calibrated due to many reasons. So there's nothing standard. And also, if you don't do it in a standardized way, there's no penalty. But if you're running as like there's in a factory, if a multi-million-dollar machine fails, then it's a problem. So it's a different problem than a problem.
So another interesting question.
So finish the students then and I'll be the last.
So he was interested in the Meadowlands project, and so he's curious if the digital twin that you're creating is only used for transportation purposes, or are there any other use cases that you see?
Multimodal transportation, basically cars, buses, and pedestrians. But we're not getting inside the stadium. You're not allowed to. So when they get out, what happens? I mean, for example, if you have 10,000 people coming in the middle of the road, what happens? How do you? I mean, it's not going to happen, but those kinds of. But we're not doing anything else. So also we're not looking at things like if it rains very heavy, because that area floods a lot. So we're not doing that. You could, but then.
Any more?
By building simulation model, how do we consider the regulations and policies?
How do you what?
The regulations and policies to be controlled by simulating a scenario,
Regulation in terms of.
like taxes, management.
So I mean, everything, all these models, they have stop signs, yield signs, left turn. So you enter all of the network characteristics into the simulation. Right? I mean, left turn allowed, not allowed. What is the signal timing? What is the warning? What is the message sign? Everything that you see, there is an object that you can use to model inside.
So for like avoiding the collisions and for near misses, there is no as such, rules we can imply in the simulation application.
So we know, for example, if people are trying to make a lane change, because they have to exit, and if the traffic is above certain level, then the risk will go up. And so we try to capture that by looking at the traffic vehicles trajectories, right? So if they get too close to each other at a higher speed, that's a high risk. So there's it's a threshold model, okay? So if they get too close to each other more than X, then I know it's a near miss. Is it actually an accident? No, but it's just an indication of what would happen if they don't pay attention. Yeah, there are more sophisticated models, but we still don't use them. So these threshold models were quite valuable.
Okay, last question from Dr. Shadvis.
Well, thank you very much. I wanted to give an opportunity for all the students to ask questions because I'm not from this area. Very insightful presentation. Thank you very much. I have some comments and some question maybe. One of them is, I think you also like to mention that you've been doing digital twin, or the name was. And I was thinking, in our own research many years ago, but I think that humanity has been obsessed with twinning somehow. Even the great Leonardo da Vinci did the twinning of a beauty, and
Yeah.
then in China, I see some Chinese doing the army in Xi'an. It's like a twin of an army,
Yeah.
not digital sense,
Yeah.
but not
Sure.
a physical sense. So I think you've been doing this, and in advances in technology, I think there's a lot of opportunity. I think one question that I have, I think you touched on it, but then you went into details in transportation. I feel the real advances will be at the intersection of not digital twinning transportation or structure, but digital world in general, especially in our civil engineering domain. If we can combine all of
Sure.
transportation, structure, infrastructure, geotechnics, sea level rise. So I think my question is how you see the next step. What's next? Where we can make real advances and meaningful advances in the digital twin world in our domain. I think that's one question. And the last comment is, I think there are some challenges in what you showed towards the end. It's not real, generated images, etc., data, etc. I think those can be solved. But I think the real problem is the trustable information in every domain when we are using AI. I think that's the problem.
I mean, that actually the last slide was about that. I mean, they look very realistic. I mean, in AI world, they're called hallucinations. Okay, so they use. So I on purpose avoid the use of words that will humanize AI because I think it's being done on purpose. I mean, AI is like any other simulation or machine learning model. So when you start using this adjectives that will humanize AI, it just creates a wrong impression that it's smart. It's like a human. It's not. So that's why I didn't use hallucination. But for the students, it would have been much more kind of. They would understand what that means. But so AI will create things that are not realistic. Not because, again, Rushan put it like a hero or villain. That's also not right because it doesn't know. It doesn't have the understanding. But as a human being, we can still look and say this is not real because you will not see something like that. So that's why you need human in the loop, and that's what we're trying to do with the LLM model. So we are trying to put but that's the difficulty. Then it becomes a labor problem because you need to have someone who will run these scenarios and then say if it's realistic or not. But that's a major problem.
So what would be, I know you work with professors from different disciplines. I know.
Yeah.
So what do you see in the next 5 to 10 years? Where, I mean, professors like you or Andy, myself, others, or other professors like Sharon, what we should be focused on? What's your vision? I would like to hear your vision, where we can come together with similar or related subdisciplines to make real impact. What would be your vision?
Okay.
Next 5 to understand. It's difficult.
No. I can be. I mean, this part is. I mean, we were talking with Shoria too. Part of it is professors should not be businessmen. Right? So we should not think like businessmen. So basically, we should get together and talk, irrespective of the field, to each other. Okay, and become friends. So when I was doing my sabbatical almost 15 years ago at Princeton, I saw something nice. So they had funding to do tea hours every afternoon for the professors. So basically, they serve tea and cookies, and all the professors come. I don't know, they come to talk to each other or for the tea, and then they write on the board. They write equations, they write ideas, and these are from different departments. Then they start understanding that like there's a problem like this one, and I didn't know that problem. Can I do it together? I think the key is basically increasing the human connection. That's what happened with Hani. I mean, Hani is a structures engineer, bridge engineer, nothing to do with what I do. The other thing is, if you're a transportation student, you should go take classes from other, at least sub-disciplines. This is very important. And the reason Hani was able to talk to me, because when he was at Michigan, he did this certificate on intelligent transportation systems in electrical engineering. So he learned about intelligent transportation systems, never practiced it, never did it, but he understood we could talk similar language. So I think that's very important. So we shouldn't put students in these compartments. So that's why I tell my students, go take classes in computer science, in statistics, in do structures. They do one class in structural health monitoring because it's sensors, it's risk, it's failure. Learn that. But because we are so optimized, we want to finish, write papers, we think that it's a waste of time. It is not. I think if we do that, I think most of the problems that you mentioned, it will happen. And also, you should just, I'm not doing it, but I have a colleague who is now not feeling very well, quite old. Yossi Barakman, every morning he comes to office and he turns off his computer and email until noon. And he reads his book, solves his equations, writes his paper in the afternoon. So you send him an email in the morning, he's not going to respond to you, right? Because he has to think. So you need to have time to think. If you do all of that, I think, but it's easier said than done. Uh, Otherwise, I see this going on. Everybody, and then also things will repeat the same things. We will reinvent the wheel many, many times because now on one danger is like there's so many papers, so many journals, nobody's reading them. So that's another problem. But you cannot do anything. You cannot tell people not to write papers. They will do that. I think what we can do if we do those three things that I mentioned, it'll be a better research environment. And don't expect practitioners, DOT and so on, do great stuff. They have their own problems. So it has to come from us.
Thank you very much for the insightful comments. Thank you all for joining. Thank you everybody on Teams for joining. And please stay on. We'll take one group picture with Dr. Oz.